Log on, tune in, find out. Another good idea from Cambridge.
All right. Thanks to the organizers for inviting me, even though I didn't come to any portion of the original program. I appreciate being able to crash a party whenever I can. All right. So this talk is going to be online. I apologize, I did not make a new talk for you guys. This is exactly the same as the one I gave at Banff, but I think there's actually a very small number of people who saw this talk at Banff and are here today. So sorry to them, or you can go to sleep. All right. So let me start with stuff that you probably all should know. We're going to be interested in, let me move that little hand over, interested in simple Lie algebras. Just for concreteness, let me say SLN. Very little that I say is going to depend on the fact that I'm using SLN, and I will note when it does. Here's my favorite presentation of SLN, and I think everybody else's, and the one that we will use. I'm not going to go over this in detail, but I'm kind of assuming that you remember this. And of course, the universal enveloping algebra is you just take this presentation and consider it as the relations for an associative algebra. And of course, there's also SLN hat, which I'll mention a few times. That's the same presentation, but you take the indices in Z mod A. All right. Something which maybe is a little less familiar to people. I apologize about the flickering. I'm not sure what's going on. Is this idempotented version of the universal enveloping algebra. So what this does is it adds idempotents that are supposed to be projectors to weight spaces. So 1 sub lambda is the projection to the lambda weight space. So the relation that tells you that is this. Hitting something with 1 sub lambda and then acting with hi acts as hi acts on the lambda weight space. This lambda super I is my personal little code for the way that hi acts on the lambda weight space. So the co-root for I eating lambda. And similarly, this just says how ei and fi change weights. And now I'm going to do something which initially will look a little weird, but will actually be important, which is this is just a different way of representing elements of this algebra, right? We can represent elements of this algebra in the way we're all familiar with. We give them names, and then we put them in a list to show that we have multiplied them. But there's another thing we can do, which ultimately will sort of lead to good things, which is I can replace each ei with a down arrow, each fi with an up arrow, and put little labels under them to remember what root they came from. And then in order to remember what the idempotents were, to remember what weight space I'm supposed to be acting on, I put little labels over this line that the arrows sit on. And this relation, how weights change when we act with ei and fi, tell me how the weights should change when I read from right to left. Right? So here I cross over an ei, and I add, an ej, and I add an alpha sub j. Here I cross over a fj, and I subtract an alpha sub j, etc. All right, so these are the operators, and these remind me what weight space they're acting on. Remember, the commutation relations between ei and fi depend on what weight space they act on, right? On each weight space, the commutator acts by some scalar, and that's exactly the information of what weight space we're on. All right, so I think none of these people are in the audience, so I don't have to be quite so Solomonic about handing out credit, but various people, Ruke probably would take the lion's share of the credit, but many other people, including Havanov and Lauda, made very important contributions, especially in sort of how to interpret and understand this picture, where they looked at, sorry, pressed the wrong button. They looked at these pictures and said, we can make these into the objects of a category. So before, these were vectors. Actually, so the difference between Schwang and Ruquier and Hovanov and Lauda is Schwang and Ruquier looked at these vectors, and Hovanov and Lauda looked at these pictures and said, we can make these into the objects of a category. We can define maps between them. So what are the maps going to be? They're going to be diagrams that interpolate between these pictures. This is why the pictorial representation is very useful. It sort of reminds us in a very compact way how we can connect these up. So some things that might initially be confusing. For one thing, these strands have to be oriented. So you can only connect an Fi to an Fi from the top to the bottom. And if you want to connect things on the same side, I didn't do this up here, but I did do it in the middle. I connected a Fi to an Ei by a cup, and then I connected them again by a cap. So this is actually a bit like John's Wald-Brauer algebra that he mentioned in the morning. I was extremely tempted to heckle from the audience and mention that you could represent the open dots as down arrows and the closed dots as up arrows, and that would exactly tell you how you were allowed to connect things. One other non-obvious thing is I'm going to allow a decoration on these, which are dots. So the dot, it's just some morphism from Fj to Fj. I'm not imposing any relations on it. It's just there. I'm imposing the relation that if I do a dot here and do a dot here, it doesn't matter what order I did them in. And in general, I'm allowed to isotope things as much as I want. Except that these crossings are real crossings. I don't just get to willy-nilly move dots to the other side of crossings or do triple moves or anything like that. Those you need to be very careful about relations. All right, so morphisms are going to be sums of diagrams of this form. I want to do everything linearly over a field. So it's going to be sums of these with coefficients from some field. And then I'm going to impose some relations. Now, obviously, this is way too many relations to take in at once. And one of the reasons I said SLN at the beginning is if I had said G, it's just some Lie algebra, these relations would be even more complicated. And I would have more trouble fitting them on one slide. I'm just putting these up here because if I say there are some relations and don't tell you what they are, you go, oh God, what are the relations like? Well, he's pulling a fast one on us. They aren't that bad. If you work with them for a while, you can keep them all in your head simultaneously, but I could explain them or I could do the rest of my talk, and I would rather do the rest of my talk. But one thing that's worth noting is there is a grading that makes these homogeneous. I won't even tell you what it is. We can discuss it later, or you can read the paper. All right. But they are homogeneous. That's important. And I admit, they look weird. Yeah?
Are they related to the break group to the phylum? Or to the phylum?
No. They actually it's more that they all kind of have a flavor like the type A braid group. So this is one of these mysterious statements like all quiver varieties are type A objects. So these algebras, they behave like type A representation theory. They don't behave like other types, even when you attach them to other types. In the same sense that quiver varieties for type D are more like type A nil cones than they're like type D nil cones. All right. So one good thing about these relations is you might say, oh dear God, where did those come from? And this might not actually be the answer for where they come from, but you can get them looking at the geometry of quiver varieties. There is a very natural explanation for where they come from by looking at quiver varieties. Okay, so like I said, I want to make these a category. One thing I'm going to do is that if you just forget this word idempotent completion for the moment, it would be what I said before. You have these diagrams on the line. Those are the objects. Morphisms between them are these pictures, k-linear combinations of them with the relations I put on the other slide. Idempotent completion just says, if I find a morphism, that's an idempotent. Well, if you find if you take a module over in algebra, and you find an idempotent endomorphism on it, the image of that idempotent is a summand. So idempotent completion is just the operation that takes a category and says, look at all the idempotents. If you have an idempotent that doesn't have an image, add a new object, which is the image of that idempotent. So one way to think about this is it's what you do to the category of free modules over in algebra to get the category of projective modules over in algebra. You look at all the idempotent endomorphisms of free modules and say, actually those have images. I'm going to add those to my category as well. And you could think of this as some huge locally unital algebra, and I'm looking at projectives over it. You could think of it that way, but it would be a very big algebra. Some people don't like locally unital algebras and prefer to think of them as categories. I'm kind of one of those, but depends a bit on the day. All right, so what else about this category? It's monoidal. I mean, the universal enveloping algebra, it was an algebra. It had a multiplication. So if I'm going to do some category thing that corresponds to that, it had better have a multiplication. Well, when I represented things in the universal enveloping algebra as these weird sequences, what did multiplication mean? It just meant put them next to each other. But you have to be a little bit careful because there were these labels corresponding to what weight space you were acting on. And if you project to one weight space and then project to a completely different, unrelated weight space, that's 0. So if I try to put these next to each other and these labels don't match up, I just get 0, right? If I take two orthogonal idempotents, their product is 0. So I put the diagrams next to each other, assuming these guys match up and I can fit them together. And you do the obvious thing with morphisms. I mean, again, I just have two morphisms, I put the pictures of them next to each other. It's as simple as it gets. All right, and the theorem is the Grothendieck group of this monoidal category is the universal enveloping algebra with these idempotents added. In sort of the most obvious way possible. And first I'll give you an example, and this is kind of the one we had before. You take this object, you think about its class, that goes here. That just goes to the corresponding element to the algebra under the correspondence we already discussed. And somehow I tried to set things up so this looked like what obviously had to happen, but this is actually a really surprising theorem because all of the relations in the universal enveloping algebra are a consequence of the relations on the crazy slide I put before. So every relation in the universal enveloping algebra has a corresponding isomorphism in this category that tells me that it holds on the level of the Grothendieck group. And again, if I had more time, I could pull those out, I could pull out the relations and exactly show you, this relation is saying that the identity on this object is the sum of a bunch of idempotents. So it's exactly telling me that this object breaks up into a bunch of direct summands. All the relations just look like that. So kind of once you know the theorem is true and you have the right relations, it's mostly just following your nose. But somehow that crazy page of relations was very carefully set up to make this happen. And it's not so easy to check. You always have to be really careful that you didn't just make everything 0. It's a very serious danger when doing anything with generators and relations, as I'm sure you all know. All right. Now I mentioned this and said it was important and didn't tell you any details about it. The relations are homogeneous. So everything can be graded. The category can be made graded. And once I've done that, there's a Q in the Grothendieck group that corresponds to grading shift. Well, okay, I took the universal enveloping algebra, I added a Q. What could it possibly be? Well, it's the quantum group, the quantized universal enveloping algebra. This, to me, is one of the great justifications for this theory, that as long as you remember things are graded, everything happens in the quantum group for free. There's no more effort involved in checking that this Grothendieck group has the right size, and very little effort involved in checking that the Q's are in the right places to get the quantized universal enveloping algebra. So on some level, and this happens over and over again at every step. The story for the quantized universal enveloping algebra just comes along for the ride as long as you remember everything is graded, which to me is kind of mind-blowing, but it does happen. I should pause. Are there any questions? All right, great. I know I'm going through this very fast, but somehow there's a lot more than an hour's worth of material here. So one has to do it at a reasonable clip. All right. So now that I have something that corresponds to universal enveloping algebra, I suppose I shouldn't have to justify this because this is a conference mostly composed of representation theorists. But obviously the first question is, after you've proved the really basic properties, what does the representation theory of this category look like? Does it look anything like the representation theory of the universal enveloping algebra? Well, as good representation theorists, what's the first thing you look for? Simple modules. So there's a very nice classification of the simple modules of SLN or any other Kac-Moody algebra. Not all of them, that's actually pretty complicated, but the integrable ones, and in finite type, the finite dimensional ones. And as we all know, it's that there's a unique line killed by all the EI, and the representation is determined by the weight of that line. All right, so how would you try to mimic that in the categorified world? Well, instead of a highest weight vector, you have a highest weight object. And the highest weight condition says the functor EI acting on this object. So I had a monoidal category. I'm going to try to construct a module category over it by starting with one object, acting on it by everything, and imposing the condition that EI acting on that guy is 0. Pretty reasonable. So I can have pictures for that look like this. So here's my highest weight object. I'm going to denote that with a red line instead of a black one. And what does it mean that it's of weight lambda? Well, it means that this region right to the left of it is labeled with lambda. It means if I try to act on it with any of the other projections, I get 0. And if I act on it with the projection for lambda, I get the same thing back. That's what being weight lambda means. So everything else hooks onto this guy by starting with lambda and then subtracting off or adding the roots corresponding to the black lines that you've added. And similarly, well, morphisms are just going to be taking a morphism from the category and putting it next to this red line. But you got to remember, when you kill an object, you also kill all the morphisms that factor through it. So this is kind of one of these subtle and interesting things about categorifying, is that, it's not just like in the universal enveloping algebra where I just killed that. I didn't just kill it, I also killed a bunch of other objects, say, whose identity morphisms factor through this guy acted on by something else. So the sort of best example of this is this loop-de-loop. So I get one orientation at the far right, I get the other orientation at the top and the bottom. So this object in the middle is dead. I fear I may have switched my convention about which one is EI and which one is FI for the up and down orientations. I apologize about that. But the point is, here's FI, and here's a morphism from FI to FI acting on the highest weight object, which is killed by factoring through something involving an E. Factoring through an object that I had to send to 0. And one of the consequences of the relations that I put up before is that this guy satisfies a cyclotomic relation. The dot on the far right strand, the one next to the red one, satisfies a polynomial relation which is monic and whose degree is the label on this strand eating lambda. Now, if you haven't thought about this stuff before, these coefficients look really weird. Let me just assume they're all 0. Those bubbles were actually formal variables, but they're formal variables that have positive degrees. So there's only one reasonable way to specialize them to actual numbers. You just set them all to 0. So let me simplify my life and do that. So instead I have this relation, that if I act with too many dots on the far right strand, I get 0. And this is a relation that, again, you might have seen before if you've worked with this stuff. It's often called the cyclotomic relation. And I mean, it both is a cyclotomic relation in the usual sense of like a cyclotomic Hecke algebra and has some interesting relations to the cyclotomic Hecke algebra. So I get a quotient category killing these objects EI. Let me call this L lambda. And the theorem is that the Grothendieck group of that guy is the right irreducible representation, and it's essentially the unique such module category. I'm fudging a little bit, but it's the unique one which is graded and where the highest weight object has endomorphisms that are the field. So that's a reasonable set of conditions to put. And this should be really surprising to you, because I took a highest weight vector, I said EI acting on it is 0. You should think that I would get the Verma module, but if you thought that, you are wrong. The additional relations that I need to cut down to the irreducible head of the Verma module just happen magically. They follow from the relations I put on that big complicated slide before. It turns out that if you act by FI too many times, you can factor that through something involving an EI in the wrong place, and so it's 0. One of the kind of incredible things about this picture is you can only get integrable representations as modules over this guy, if you only use highest weight things. So you just cannot get Verma modules. It can't happen. Which is almost a little sad. I like Verma modules. But on the other hand, this tells you that this is on some level a very nice thing. It picks out the absolute nicest part of the representation theory of the universal enveloping algebra automatically without any extra effort on our part. So that's kind of brilliant, actually. All right. So one of the things I'm going to try to bring in the second half of my talk, which I'm not even in yet, I'm going through this pretty fast, is why do we care? Why would we want something like this? Well, one answer is categories have a very nice distinguished set of objects. So the category I introduced to you, it's an additive category. I don't have kernels or anything like that. The only thing I have are, I know that if I find an idempotent, I have an object that it's its image. That's about the only thing I know about it. And I can take direct sums. But it has a nice sort of set of generators of the Grothendieck group, which are the indecomposable modules. This category is Kroll-Schmidt, so everything has a unique decomposition into indecomposables. So indeed, they're a basis of the Grothendieck group. And if I multiply two of these, then I get a sum of indecomposables. So this is a basis of U dot with positive integral structure coefficients. In particular, acting by EI and FI, and U dot, or on this representation, has positive integral structure coefficients. And of course, we know some other bases for representations and for U dot that have positive integral structure coefficients. And indeed, one gets Lustig's canonical basis for the representation. This is not written up anywhere, but it's also true that you get the canonical basis for U dot if your algebra has symmetric Cartan matrix and the characteristic of the field is 0, which is reasonable conditions. With the symmetric Cartan matrix thing, so like I said, this is about the only place where the type of the algebra plays an important role. Somehow, proving this theorem requires geometry, requires using quiver varieties, which was done by a couple of members of the audience. And so if you don't have symmetric Cartan matrix, no quiver varieties, or at least a much more complicated theory of quiver varieties, where you can't get the positivity that you need. And in fact, as is well known, in non-symmetric type, Lustig's canonical basis doesn't necessarily have positive structure coefficients. In other types, there's some kind of trade-off between positive powers of Q and positive integral structure coefficients. And Lustig's basis goes for positive powers of Q. This goes for positive integral structure coefficients, so they have to part ways. All right. I would also comment, one of the reasons these are interesting is they give a new perspective on categories representation theorists already thought about. So if K is characteristic 0, then the representations of all symmetric groups at once categorify the Fock space representation of SL infinity. And you can get the fundamental representations of SLN inside that by just being careful about what bit of SL infinity you grab. On the other hand, if K is characteristic P, then the projective modules over symmetric groups, you'll note I say the categorification. There's only one. There's a unique one, and indeed, it's the symmetric groups over field of characteristic P for SLP hat. So this takes a category that many people care about, modules over symmetric groups, and realizes in a completely different way. And this is maybe the bit that one should really ascribe to Brennan and Kleschab, that the thing I wrote down before, all these crazy relations, are a presentation of the symmetric groups if you choose the right field and stick in the right parameters. That was a theorem proven by direct computation. Actually just finding elements of the symmetric group that satisfy the right relations. On the other hand, there's sort of a similar situation where the field is characteristic 0, and you look at Hecke algebras where Q is an nth root of unity. And that is the categorification of the basic representation of SLN hat, where K is characteristic 0. I mean, somehow you'll note I said there was only one, and then I said two things that categorify these representations. The difference is the base field. And in all cases, EI and FI are exactly the functors you would think, the I restriction and I induction functors. Now you might think that this is just sort of playing a game, rearranging deck chairs, but this bit was an extremely important point in the proof of the Brouet conjecture by Schwang and Ruquier, and is arguably what sort of got the ball rolling on all of this stuff. So I mean, that's not something I'm going to talk about, but I think it's a good justification for why this is a valuable and productive way of looking at things. That this gives us a new perspective on these old categories. The other thing, I mean, sort of what got me interested in this story is that, well, the reason people started studying quantum groups was to a large degree that they appear very naturally in topology. So you start with a quantum group, its category of representations has this nice structure, it's a ribbon category. So what that means is, so representations of quantum groups, I can take tensor product of them, but if I do that in the opposite order, it's not canonically the same. There's an isomorphism from V tensor W to W tensor V, but in fact there are many. And in particular, there's one that's kind of attached to a naturally to an overcrossing, and one that's naturally attached to an undercrossing, and suddenly knot theory appears. I apologize to the topologists in the audience that I'm not going into more detail about this, but this is sort of one of the real inspirations for the study of quantum groups was to understand knot polynomials. So there's one attached to every representation of every quantum group, I should say for a finite type Lie algebra. This somehow uses in a very fundamental way that you're finite type. So what we have up here are these two categories. And what we want to get out is knot homologies that categorify these. So this is going to be a bi-graded vector space, or a chain complex of graded vector spaces, where the graded Euler characteristic is the knot polynomial of interest to us. Well, you know, somehow you'd like to do this by saying, this is such a nice category. The category of two representations over it has some nice structure, which matches up with the structure of UQG representations. You want to say that this is a ribbon 2 category. At the moment, it's not really understood what that means. And in particular, we're a very long way from proving any version of this statement. Ruquier has given some talks about possibly defining what the tensor product of two U representations is. But at the moment, even that isn't written up. And then you would have to produce some huge number of compatibilities between all the structure maps that you would need to write down. So even when we have an abstract tensor product, which is still in the works, we're still going to have to check a ton of things before we can really say that this thing exists. But we can kind of fudge, or I can kind of fudge. So you can very explicitly, and I will very explicitly, write down a category that corresponds to the tensor product of some simple representations. And this is really very much, you take a list of highest weights, and I tell you a diagrammatic category, and that its Grothendieck group is the right thing. So this doesn't involve doing a kind of functorial construction where I feed in two representations and smash them together in some way. It's instead just saying, okay, this feels like the right thing to attach to a tensor product, and oh look, it has all of the things that we would want. So let me try to describe this. Okay, so our starting point for the universal enveloping algebra was to have a graphical description of the elements which we could then turn into objects and define morphisms between. So what I want to do for tensor products is do a similar thing. So acting by Fi or Ei, I'm still going to denote with black lines in exactly the same way I did before. And then I'm going to add a new thing, where a red line labeled with lambda means add a tensor factor with highest weight lambda, and take whatever vector you were working with and tensor it with the highest weight vector in there. So you can think about what we were doing before as, for simple representations, as kind of begin with the void, or not the void, the trivial representation, denote that by kind of nothing. And then I add this red line lambda to tensor with v lambda and take the highest weight vector. And then when I put a black line to the left of this, I'm acting on the whole tensor product. So for example, here I start with something from lambda 2. I act by fj on that. I add something from lambda 1, and I act with ei on the whole thing. Not just on this tensor factor, on the whole thing. So this is a little weird in that I'm doing something that's very not symmetric, that really favors one side of the tensor product over the other, which maybe is a little weird, but on the other hand is kind of the whole point of quantum groups, right? Like what quantum groups give you is they don't treat the two sides of the tensor product equitably. And so it kind of matters which order you flip them in. So on some level, this is kind of promising. Also, Lustig's canonical basis for tensor products doesn't treat the two sides of the tensor product equitably either. It somehow shows a preference for one of them in a very similar way. So this should also tell us we're kind of on the right track. We should add some more relations. As before, I just put these up to show you that they're not so horrible, but they are a little bit horrible. And indeed, the theorem is what we expect. You get the right Grothendieck group when the Cartan matrix is symmetric and the field is characteristic 0. The indecomposables give you Lustig's canonical basis. And this is what you can use to prove that Lustig's canonical basis of U is given by the indecomposables. In finite type, in infinite type, you have to use some other arguments that are not written up and for all I know might be wrong. I'll also mention in non-symmetric type or positive characteristic, you just get a new basis. For tensor products, for the irreducibles, for U dot, it's just something different. And nobody else got around to giving this a name, so I decided to call it the orthodox basis because I believe it is based on the correct doctrine. And this still has the very nice property that it has positive structure coefficients. For example, totally non-negative elements act with non-negative structure coefficients, et cetera, et cetera. And the kind of other thing that's important about this category, which was the whole point of producing this, is after I replace this guy with its homotopy category, then there are functors categorifying the maps attached to any tangle that respect tangle decomposition. So if I have two different tensor products, I didn't draw a picture of this, maybe I should have, and a tangle attaching the tensor factors. And I mean, this should remember overcrossings and undercrossings because I'm in a quantum group. This is the sort of thing that the theory of quantum groups attaches maps between representations to. Here, we attach a functor between these categories to such a tangle and prove by slightly unpleasant by-hand computations that this does not depend on sort of how you present the tangle and respects tangle decomposition. In particular, you could feed in a link thought of as a tangle going from the empty set to the empty set. And what you get is a functor from the homotopy category of graded vector spaces to the homotopy category of graded vector spaces, which must be tensor product with a graded complex of vector spaces. And that's a not homology. I mean, unfortunately, the actual computation of this is still kind of horrible, right? Kind of the thing you want to do for each tensor factor is not so bad, except that you describe this by kind of saying, well, what did I do when I said homotopy category? Really, I kind of thought, okay, these are the projective modules over some algebra. Let me work with all modules over that algebra. So I'm thinking, that's really a projective resolution of some module. And you kind of define these functors by taking derived functors of tensoring with various kinds of explicit bimodules. And so what you're doing involves a lot of taking projective resolutions. And as I'm sure many of you can attest, taking projective resolutions is really freaking hard. It's just a complicated thing to do, and so it's very hard to do any computations. Anyways, I'll stop stepping on my results now and move on. So again, these are somewhat familiar categories. For example, if k is characteristic 0, and I'm always talking about fundamental weights here, but somehow, I mean, the categories for non-fundamental weights just sit inside the ones for fundamental weights. So somehow, like, if I talked about non-fundamental weights, I would just say, take this crazy subcategory of what I was going to do for fundamental weights. Anyways, if k is characteristic 0, then for SLN you get a sum of blocks for parabolic category O for GLK, where k and the parabolic depend on the choice of weights. So this is, you take your list of fundamental weights, you think of it as a composition, you think of those as the sizes of blocks of block upper triangular matrices, and you look at that parabolic category O. John in his talk mentioned that sort of level 2 things, that would mean 2 fundamental weights, have to do with parabolic category O for block upper triangular matrices with 2 blocks. So this is kind of a generalization of that.
Is this sort of regular blocks or mostly singular? Or?
Mostly singular. So I said sum of blocks. The central character depends on the weight space. So you maybe shouldn't hold me to this, but I believe, yeah, it's going to be mostly singular. So, you know, for example, you're going to have a highest weight space, which is, of course, the extremely singular block that only has one thing in it, that sort of thing. I mean, this is all based on work of John and Sasha, like their higher Schur-Weil duality business. So they had, they didn't quite say this in their paper, but they had a categorification of the simple using self-dual objects in these category O's, where again, the weight spaces of the simples were the different central characters. And so I'm using exactly the same central characters and just saying, well, if you take all the objects, you categorify the tensor product. All right, if I do this for SLN, I get the category of some projective modules over a cyclotomic Q-Schur algebra. So what happens? Somehow, right, if I took just a highest weight for a fundamental representation, I would be getting representations of the symmetric group, which are the category of some projective modules over a cyclotomic Q-Schur algebra. They're the projective modules over a Q-Schur algebra, a normal Q-Schur algebra, that are in the image of the adjoint to the Schur functor. And those are, for the Q-Schur algebra, they correspond to partitions that are n-regular. Here it's going to correspond to multi-partitions where all the constituents are n-regular. And it's well known, at least to many people, that the set of multi-partitions where all the constituents are n-regular has a crystal structure, which is the tensor product of these crystals. And that's sort of the important fact for seeing that these are the right things. But if you want to get all projective modules over a cyclotomic Q-Schur algebra, what you should do is think about what would happen if you used GLN hat instead of SLN hat. So this is a work in progress with Katarina Struppel. We're basically done. There are people in this room who can testify that the actual paper exists, and we have sent it to them, but it's not on the archive yet. So I'm cheating here, I'm skipping a lot of details, but there's a way to make this picture work for GLN hat. And when you do that, you get a cyclotomic Q-Schur algebra. Even better, you get a grading, an unexpected grading on the cyclotomic Q-Schur algebra, which is compatible with John and Sasha's unexpected grading on cyclotomic Hecke algebras. Right, So that's exactly what I was saying. All of these realizations of classical categories in terms of higher representation theory suddenly create gradings where there weren't necessarily gradings before. I mean, the grading, of course, on category O for GLK has been known for a long time, but it is highly non-obvious. So this is an explicit graded presentation of this parabolic category O, which is, I think, a new thing. But for example, for cyclotomic Q-sure algebras, I'm pretty sure that this is new. I mean, so Ariki had proven that there was a grading on the normal Q-sure algebra. This kind of extends that picture, but also is a bit more explicit, actually gives a graded presentation of these things, sort of. I'm lying a little bit when I say presentation, but an algebraic description. So one of the things that follows from this is that the decomposition numbers in all of these pictures suddenly have Q analogs. So one that, again, that's been known for a while is that the graded decomposition numbers of parabolic category O are the coefficients of the canonical basis of a tensor product of minuscule SLN representations. So you take the canonical basis, you expand it in the standard basis, and what you get are Kazhdan-Lustig polynomials. All right, so for a Hecke algebra to an nth root of unity, these are the coefficients of the canonical basis of a basic representation in terms of the regular wedge basis. I believe this is a result of John and Sasha. And finally, one that's a result of Katerina and I in this paper, which is coming out soon, is that the graded decomposition numbers of a cyclotomic Q-sure algebra are the coefficients of a canonical basis of a tensor product of Fock spaces in terms of the wedge basis. And some people might object to the canonical basis. So part of our picture is defining a bar involution on a tensor product of Fock space, level 1 Fock spaces, and then showing that when you plug that bar involution into the usual definition of a canonical basis, the projective modules over the cyclotomic Q-sure algebra correspond to the canonical basis. I feel like there was something else I was going to say here, but it's slipped my mind, so I guess we should move on, unless there are any questions. Okay, 10 more minutes. Excellent. I can do 3 slides in 10 minutes. All right, so everything we've done up till now has been kind of a combinatorial perspective. Everything is done by hand. Anytime you want to do something like a comparison to classical representation theory, you go look up someone's paper, for usually John and Sasha's, that has actually done some computation of what this algebra in classical representation theory is, and you apply their theorems. So what I want to talk about more briefly is something that, again, hasn't been published, but which is in the works, and I think I can actually claim our theorems, which is, instead of the combinatorial perspective, to use what I might call an algebraic perspective, getting representation theory not of finite dimensional algebras, but infinite dimensional algebras, things like universal enveloping algebras. So attached to a sequence of weights, we have a quiver variety with a C-star action. I'm not going to define this. This is in Nakajima's paper, Quiver Varieties in Tensor Products. The quiver variety is symplectic. The C-star action is Hamiltonian. And there's a natural universal deformation quantization of this quiver variety. I am, again, not going to get into what this is, but there's a theorem of Bezrukov, and Kaledin that there is a sort of unique best way of doing this. This somehow comes from the fact that this is symplectic. It's much easier to do deformation quantization of things that are symplectic than just some random Poisson structure. And the C-star extends to an interaction on A, right? You take the function that was the moment map for this Hamiltonian action before, you upgrade it to an element of this deformation quantization, and the action of that is the action of the Lie algebra of C star. All right, so this category corresponding to L of lambda is actually going to be a generic block of category O for this algebra, where category O means I look at the non-negative weight subalgebra of the deformation quantization and look for things that are locally finite with respect to it. And the action of U is going to be tensor product with certain Harish-Chandra bimodules over this algebra A. So this is, again, what I would call an algebraic description. It's sort of realizing things in a way that looks more like classical representation theory of, say, groups. But remember, this is kind of weird in second order. We're taking something which is vaguely reminiscent of a universal enveloping algebra, looking at its representation theory, looking at the Grothendieck group, and seeing that that Grothendieck group is something interesting from representation theory. And I mean, you've seen these sort of second order things in some earlier papers, you know, say of John and Sasha, who I keep citing, but because they did very important work in this field, where they looked at, you know, finite dimensional representations over W algebras and found that those categorified some interesting representations, which you can see as a special case of this whole business.
And what should I think of these Harish-Chandra bimodules?
What you should think of them is, so Nakajima tells us that U of G acts on the cohomology or constructible functions on these quiver varieties by convolution with certain correspondences, which are Lagrangian in the product of the two quiver varieties. So these bimodules quantize those correspondences in a very precise way. I mean, it's really like, you know, you think of it as a symplectic reduction of a cotangent bundle, and you look at some constructible sheaves on the zero section of the cotangent bundle, and you hit those with Riemann-Hilbert, and then hit that with non-commutative Hamiltonian reduction, and that's where these bimodules come from. It's very much that this is sort of upgrading Nakajima's construction to the representation theory of the deformation quantization. Does that answer your question? I mean, I think that's as much of an answer as you're going to get in 2 minutes. All right. So one particularly interesting case of this is that if you take quiver varieties of affine Dynkin diagrams corresponding to the basic representation, then those deformation quantizations have appeared in other contexts. They're spherical symplectic reflection algebras. 4 special dimension vectors. You take the basic representation and act on the highest weight vector by multiples of delta. Those have associated quiver varieties. Those quiver varieties are symmetric powers of C2 mod gamma, and they quantize to be spherical symplectic reflection algebras. So if you apply the theorem on the page before, in this case, what you get is that finite dimensional representations of the symplectic reflection algebra are derived equivalent to the weight space of this unique quantization of the basic highest weight representation. Again, there's only one of them. It's a unique quantization, so there's only one way that these guys could get quantized. Sorry, not quantized, categorified. I mean, you can do this more explicitly and really see that they match up. But there's just no other way it could come out. Once you know that this 2 category U acts on the category of finite dimensional representations, there's just only one option. So what you get is the K group of this guy is a weight space of this basic representation. The Euler form is the Shapovalov form, where I'm computing Euler form over the entire symplectic reflection algebra. And the simples are Lustig's canonical basis for particular choices of parameter. Yes, good, I did say that. For certain choices of parameter, the simples are Lustig's canonical basis. For other choices, they're just something different. There's some weird derived equivalence that happens, and what corresponds to simple modules just changes. So I should say this is very much in progress. It depends on a paper of Kevin McGurty and Tom Nevins that went on the archive like last week, and some work of myself with Braden Licata and Proudfoot that also has not been published. So this is, you should treat this as a little speculative. But it is true, and once you know that U acts, it follows instantly from Rouquier's uniqueness results on categorical representations. And this can be upgraded a little bit when this group gamma is Z mod L. In that case, the symplectic reflection algebra is a Cherednik algebra. So the important thing is that if you look at the symplectic action of Z2 Z mod L on C2, there's a commuting Hamiltonian C star action that scales one of the, scales the x-axis one way and the y-axis the other way. And you don't have that for a dihedral group. There's no C star that's Hamiltonian and commutes with it. So the existence of that allows us to define a category O, something bigger than finite dimensional representations. And, well, the theorem on the page before said it was derived equivalent to representations of a rank n Hecke algebra specialized at an Lth root of unity. So taking category O allows us to replace Hecke with Schur. So it's derived equivalent to representations of a rank n Q-Schur algebra, where Q is a primitive Lth root of unity. And I'll note I'm taking integral parameters here. There should be a big flashing red light for everybody who thinks about Cherednik algebras, because everybody knows integral parameters are terrible. I mean, I don't know that, I like them, but somehow this is not usually what people thinking about Cherednik algebras think about, but somehow from the geometric perspective, it's the easiest thing. And let me just trace through the consequences that I said before. Its K group is going to be a weight space of a level 1 Fock space for GL L hat, with Euler form the usual form on Fock space. And again, for some parameters, the simples are Leclerc and Thiebaud's canonical basis. And for some other parameters, there's some weird mixing up that happens. So this depends on the work with Katerina that I mentioned before, which is not quite public yet, but which will be very soon, and I would be happy to send to anyone who cares. I just want to mention, this sounds very similar in flavor to these theorems of Rouquier and Jean-Vassero that relate representations of Cherednik algebras to Q-Schur algebras. But those of you who know these theorems also probably looked at this and went, wait, that's not how the parameters are supposed to match up. And the reason is because this is causal dual to those results. When I say derived equivalent, at least for certain choices of parameter, that's gotten by looking at simples, looking at their X algebra, and seeing that it's the graded version of the Q-Schur algebra. So it's kind of dual to these other results, which is good, it's complementary. And I haven't done this yet. Like I said, this is all kind of a little speculative and rough at the moment. I suspect with a little more effort, this can be expanded to a new proof of Eddinghoff's conjecture on the filtration of K groups for symplectic reflection algebras and Cherednik algebras, which was recently proven by, I believe it's Vassaro, Varaniello, and Sean, which sort of, this picture should is good because if you look, well, you guys will see Eric's talk in a few days. Somehow, you start with this Fock space, and then the GLL hat disappears, and you go through rank level duality. So this keeps the GLL hat and looks at how that acts, rather than looking at the rank level duality. All right, thanks.
Much. Other questions, comments?
Yeah.
Sorry, you said you didn't want to talk about computation, but any progress on computing sort of invariants of the unknown?
Sadly, no. I don't know. I need to get some graduate students or something. I mean, yeah, it is sad, but what Jake is referring to is, in almost all cases, I do not even know what the invariant of the unknot is. But I do know that if you take the three-dimensional representation of SL2, it is infinite dimensional. So it's a big infinite dimensional thing whose Euler characteristic happens to converge to q squared plus 1 plus q to the inverse t through whatever bizarre coincidence. Don't ask me why. And in basically all other types, the invariant of the unknot is a gigantic, complicated mystery. So I mean, obviously, it would be nice if that could change. And what I've dreamed of doing, but have not actually achieved, is somehow tweaking the definition a little bit to get, instead of something huge and horrible and complicated, polynomials mod t to the 3, which is kind of what you would expect when you look at the graded Euler characteristic q squared plus 1 plus q to the minus 2. Everything's shifted, so you should think of it as 1 plus q squared plus q to the 4th. That really makes you think it's polynomials mod t cubed, and I assumed it was before I did the computation, and I was wrong. So hopefully one can tweak the definition a little bit and get something that, I don't know, has some spectral sequence coming from the invariants I've defined already that cancels out all that horrible infinite stuff. Maybe it's possible, maybe it isn't, I don't know. At the moment, it's just kind of a dream. So that's actually about all I have to say, unfortunately.
Could you try to trace once more a bit how this grading on these algebras somehow comes about from your categorification? Where do you see it in the categorification?
Well, I mean, the interesting thing is, I mean, maybe I gave the wrong impression in here. For almost all classical things, what one actually does is goes and reads John and Sasha's paper about, it's called whatever, something like blocks of cyclotomic Hecke algebras and Havana-Vlado-Ruquier algebras, so some variation on those words. And they prove by hand, with very painful computation, that the Hecke algebra, any cyclotomic Hecke algebra, has a graded presentation of a particular form, and it's really, look at these elements, they satisfy these relations, give them these gradings, the relations are homogeneous. So it's a very explicit thing, and I think all examples I know kind of run through that. Or these sort of geometry pictures where one realizes that the category is actually perverse sheaves on something and figures out some way of using geometry to get a grading. I don't think, I don't think there's anything other than those. And I mean, you know, that second approach appears again in, for example, this stuff I was talking about at the end. That it's taking algebra, well, I don't know. That's actually slightly dicey to say that. I mean, it's taking algebras you understand and looking at X algebras and seeing that they're things you already knew about, which is also interesting, but is maybe a little different from the question you were asking. So unfortunately, at the moment, the answer is you do very explicit computations. I mean, for example, this work I mentioned with Katerina is very much, you know, somehow you could say that the key thing is to massage John and Sasha's isomorphism so that the permutation representations become obviously graded. I mean, there's more in that paper, I would say, but on some level, that's where the grading comes from, is you just use theirs not quite as a black box. You have to remember what it is, but you use their formulas and sort of choose things correctly so that permutation modules become graded, and so the Q-sure algebra becomes graded.
Other questions? And let's thank the speaker again.